So welcome back to the class Computational Neuroscience, Neural Dynamics of Cognition. I talked a little bit about experimental data related to decisions, but now let's turn to the theory of decision dynamics and we'll work with populations of neurons that share inhibition. So here is the basic model. I have one population of excitatory neurons that would indicate left movement or a saccade performed to the left, and I have another population that would indicate a saccade to the right or a movement to the right. Now each of these neuronal populations has interactions with itself, so neurons communicate with each other inside a population, but each of these excitatory populations also sends activity, it sends spikes to a further population, and this population is the inhibitory population. Now for this inhibitory population, I will have no lateral interactions, so there's no self-feedback, but the inhibitory population will send spikes, will send activity symmetrically back to the other two populations. So now let's look at the activity of this population here. The activity depends on the membrane potential, more precisely on the input potential, the part of the membrane potential that's caused by the input. And we use the differential equation for the population activity. So we can say the derivative of the input potential, the temporal derivative, is given by a decay term. Then the external input into this population that we are looking at, my first population here. Then it depends on the self-feedback, that's this term here, the self-feedback. And what's sent over here is the activity, but the activity is given by the input potential. So I can, f of h1 is the activity of that population. But then this population also receives input from the inhibitory population via these links here, and this would be the activity of the inhibitory population. Now I can repeat the same argument for the second population. The second population has self-feedback, it receives input from the inhibitory population, external stimuli, and its differential equation will have a decay term. Now, in order to proceed with the analysis of these equations, I make two assumptions. The first one is that this activity function for the inhibitory population is just linear. So I just take a linear line here instead of this full bended curve. Now, this is an assumption. This assumption would be valid in some limited regime. Okay? Now, the other assumption is that I say the inhibitory population is in fact fast. So what does this mean? For the inhibitory population, we have an equation very similar to this one here. So let me copy this here. It has a time constant for the inhibitory population, and I have ddth for the inhibitory population. I have the decay term for the inhibitory population. I have no external stimulus for the inhibitory population. That's a further assumption. And then I would have the input to the inhibitory population coming from the excitatory population, which would be f of h1 of t plus the input from the other excitatory population, f of h2 of t. Now my assumption is that, with assumption 2, that the inhibitory population is fast, and I express this by saying the time constant for inhibition is much, much smaller than the time constant for the excitatory population. And this means that while the excitatory population evolves, the inhibitory population can always rapidly approach a state that's quasi-stationary. So we can set at each moment in time on this slow time scale on which the excitatory population evolves, the derivative is 0. Now I bring that, so I have a 0 on the left-hand side. I bring this to the other side, and I can say H inhibitory is equal to WIE f of H1 plus WIE f of H2 of t. And this is true for all points t, where t is now the slow time scale on which the membrane potential of the excitatory population evolves. So this is my second assumption. Now the first assumption was that H inhibitory of t is the same as f of H inhibitory of t, because this function here is linear. Okay? And so this is now what I exploit here. This is the same as H inhibitory, but H inhibitory is this. So because of assumptions 1 and 2, I can write this as WEI from inhibition to excitation. And then I plug in this term, so I have WEE f of H1 of t plus, I copy this, WEI, WIE. I have this, I take this, f of H2 of t. So this is 1 and this is 2. And the rest I just copy. Minus H1 of t plus I external for the first population plus WEE f of H1 of t. Now let me continue with a few remarks. So this is the connection from excitation to inhibition. So this is a positive term. This is from inhibition to back to excitation. So this is the inhibitory coupling constant, which is negative. So overall, I have here something which is negative, because it's a multiplication, and therefore I write this as a new parameter minus alpha, with a positive alpha. Okay? Second remark, I see that I have here f of H1, and I have the same f of H1 here again. So I can sum this up. I can say I have plus WEE minus alpha f of H1 of t. And then I have here f of H2. And this is the same constant as before, so it also gives the minus alpha. I copy the rest, H1 of t. This is the external input into population 1. I can also describe this as a external input potential, a contribution to the total input potential. And on the left-hand side, I have just my ddt H of t. So this is now my equation for this first population. And I can repeat exactly the same calculation for the second population. The result would look like this. It's the same equation, just with indices exchange. Wherever I had H1, I write H2 and vice versa. Now, what has happened? We started off with 3 populations. We had 2 excitatory populations and 1 inhibitory population. Now, by these mathematical tricks that I've used on the previous slide, I was able to remove the inhibitory population. It has disappeared. And instead, I have an effective inhibitory coupling between the populations. So it's as if population 1 has an inhibitory influence on population 2. That's this term here. Population 1 has a negative influence on the input potential of population 2. And the same holds in the other direction. Thus, we have been able to reduce the number of equations from 3 equations to 2 equations. And these two populations compete. If one population shows high activity, it will inhibit the other population, and vice versa. Now note that this is an effective inhibitory interaction. In reality, excitatory neurons never send out inhibitory interaction. And that's why we started with separated excitation and inhibition. But the mathematical manipulations show that this excitatory population can effectively inhibit the other one. And that's why the two populations compete.